Okay, I think we're ready. What we're going to do today, this is actually the last of our talks. So, the last one for the Engineering 220 course, anyway. And we're going to do one that's a little bit different from the others. This one is talking about stress concentrations. We sort of touched on that when we did some of the SolidWorks simulations. You could see these stress profiles where it wasn't all just one stress across the entire part that we were modeling, and so that's kind of what we're doing here. Um, all the calculations like sigma equals force divided by area or flexural stress mc over I, all of those calculations that we've been doing, they give us a average stress calculation. So kind of this um, number that you can use to kind of get a feel for the average stress in some part. But if it's the average, then that means somewhere in there, there's at least some portions of the object that are under more stress. And that's what we're going to do here with these stress concentrations. You could simulate these objects, put them in SolidWorks, but it's always good, even if you have some finite element solver like SolidWorks or something in Fusion or ANSYS or something like that, then it's still good to have a manual way to calculate these that will go in and compare the values that you might get from a simulation to stuff that you can calculate by hand, just to make sure that you don't have some weird thing going on with your simulation. So that's what we're going to look at today, is how do you do stress concentrations by hand. And what it's going to involve is, you kind of see on the screen here, this little chart. There are going to be a whole series of charts similar to this one that we're looking at here, and they will take certain geometry, certain features, maybe a hole in a plate or a shaft with a notch in it, or a piece of plate that has a large section and a small section. So some kind of geometry, general shaped geometry, and use these charts to figure out what the highest stress. We're not going to get like this whole stress profile all across the part. We're just going to calculate the highest stress that we would expect in that part. So let's look at some of this. I think the simplest way to do these will be to go in and probably just work. Actually, we probably need the web page, don't we? Work some sample problems. So let's see if I can find one. I had one. Here's a little sample of some of the charts that we might use. Now this one's got writing all over it and everything, but there are 4 different charts here. I believe in your reference materials for an exam that we would have, these are the 4 that show up on those reference materials. Obviously, you can have way more charts out there than what these are, but this top one is used for a flat bar that has an axial load. So the loading situation and the geometry both matter on these charts. So you have to match the load type and the geometry features. So this top one here would work. Let's see if we can zoom in. This top one here would work for a flat bar that has either a hole punched in it or it has a step down of some sort, but it's a flat bar. This one over here, they kind of shaded in. This is a torsional type thing so it's a shaft with a step down on it. And it would have a torque applied to it. You can't really see a torque, but obviously it would have a torque. This one you can actually see the load is an axial load on it. The left one here is a flat bar that has a bending moment. And then you've got a flat bar with a notch and a bending moment. So those are a couple of different options that you might have, and there are many more. So we'll use some subset of these in our problems. So we're going to look at this problem first. We've got one of the flat bars. We have some dimensions on it. We've got a certain thickness, 10 millimeters. It has an axial force, and it's got a fillet right here. So this fillet is where the stress concentration is going to occur. Anytime you have a transition in geometry, so a large section to a small section, or a sharp corner, or a hole, some kind of change in your geometry, that's where the stress concentrations are going to occur. So this one, at this fillet, we don't know if it's the fillet on the top or the fillet on the bottom, but we're going to calculate the maximum stress that would exist at one of those fillet points. So the problem statement here, let's see, it says we want to figure out what's the largest axial load. So we're actually doing more of a little bit of a design problem instead of an analysis. I guess it's still also an analysis on the load side, but we're not really designing any dimensions or anything. But the largest axial load, which can be safely supported, so we're going to have some kind of factor of safety. In fact, it says right here a factor of safety of 2. And it doesn't say what the factor of safety is to be measured against, yielding or ultimate strength. But, oh, well, look here. This material is brittle. So if it's a brittle material, it really doesn't have any yield point. It just breaks. So we just have the ultimate strength of 248 megapascals, but we want a factor of safety of 2. So we're going to take that strength and divide it by 2, and that will be our allowable stress. So let's solve this the way we normally would, and then we will do the stress concentration. So I want to copy this, paste it over here, and let's get it where you can see that. There we go. That's actually a little bit large, isn't it? Let's make it a little smaller so we can get it all on there at once. Let's move it over above me. There we go. All right. So what we've got here is, first thing you do is you calculate the stress just like you would normally. So this is an axial force. I'll kind of go in and, there's the force that we're actually trying to calculate this thing. So we want to know what's the maximum force P that we can apply to this thing. It has a 60 millimeter section and a 40 millimeter section. So if we're thinking about axial stress, then the 40 millimeter section is going to have a higher axial stress or normal stress in it. Assuming it's the same thickness everywhere, which it is, it's 10 millimeters thick everywhere in this bar. So if we were to calculate the axial stress, say, in a little piece right there, we would have sigma equals force over area. Force is what we want to know, actually, that's P. And the cross-sectional area is 40 millimeters times 10 millimeters. So we could, we also know sigma allowable equals, I believe it was 248, but let's check. 248 megapascals. So 248 times 10 to the 6 pascals, but we wanted a factor of safety of 2. So we're going to divide that by 2. So 124 times 10 to the 6 pascals. So we could solve for P there, just like we had been doing before. So we've got everything known except for the force P. But what we want to do is we want to also include the fact that at these radiuses, well, they'd be better called fillet. At this fillet, there is a stress concentration factor. So that's what we want to find, is we want to find that stress concentration factor. So we've got something that looks like this setup here. And it says that we've got 5 different traces on our graph here. This one here is labeled circular hole. That would be for the picture on the left, so a flat plate with a hole punched in the middle of it. So that's not what we're doing, so we don't need that one. All of these other 4 are labeled fillets. That's what we have. It looks, maybe you've seen that word before and it was fillet. This is a fillet, not a fillet. So we need to find which one of these traces do we need to be looking at. And you take D over D. For us, we have to compare here. The uppercase D is 60 millimeters. The lowercase d is the smaller, maybe the tang or the tongue or the smaller section, 40 millimeters. And so that ratio is 6 to 4. So we'll just take and divide that. Whoa, what have I got going on my calculator? Some weird stuff. So 1.5. And that will show us that we need to use that one of the traces. So that is the second one down. Well, the second one after we ignore the circular hole. So that's the first thing, is figure out which one of the little traces you need to be operating from. If it ends up that your ratio here is between traces, then you can interpolate between them if you want to. I suppose you could just read off the graph, just kind of guess. You could do that too. It'd probably be better to interpolate. All right. The next thing I need to know is where am I at on the x-axis? And so this is the ratio of R over D. So for us, R is the radius of the fillet. They actually give us that up here, 10 millimeters. D is the same value it was before. It's the 40 millimeters. This is the lowercase d. So we've got the ratio of 10 to 40, 1 to 4, so 0.25. So what I do is I find 0.25 on my chart, and I intersect that with the trace that I was looking at. So that'll go here, and it is really close to landing on a K value of 1.6. It's probably a little bit above that, but we'll call it 1.6. So K is, from our chart, 1.6. That is the stress concentration value, and it is a multiplier. So it is the regular stress you would calculate that we did earlier here. We never calculated it, but the equation that we used, and then multiplied by this multiplier K, will give us the largest stress that we would expect somewhere around that fillet. So now we could take that idea, and we've got our equation that says sigma allowable, which is, let's get a little more room. There we go. 124 times 10 to the 6 pascals equals K, 1.6 times P over the area that we were calculating earlier as 40 millimeters times 10 millimeters. So 0.04 meters times 0.01 meters. And the only unknown in that equation will be P, and we should be able to solve for it. So let's see what we get. 124 million. Let's divide by 1.6. Let's multiply times 0.04 and 0.01. And I get P 31,000. Let's see our units. We've got everything in meters, pascals, so that should be newtons. So 31 kilonewtons. Let's just check and see if that is indeed the right answer. 31. Oh, you're not looking at that, but all I did is checked out that it's 31. And the units on that are kilonewtons. I never plug it in, but there we go. 31. All right, so that's pretty straightforward. That's kind of how these problems work. Let's do another one. And I think that's probably the best way to go about solving these, is just to do a couple of different ones so that you can get some practice. You have a homework set that's a little bit different ones from these, and there will probably be one of these on the exam 3, I believe, but I'm not 100% sure, but it's often there's one of those on there. All right, so let's copy this picture and do this one. By the way, I'm doing optional 3. These are problem 16, and this one is problem 17. The one we just did was 16. These are really coming in quite large today, so I'm not sure why. I guess I'm zoomed out differently than I have been. We need the text that goes with this. Let's see what it says. The beam shown, well, let's look at it where you can see it. The beam shown is subjected to a load of 180 newtons. So this is going to create a moment at this notch back here. If the grooves, so those little notches towards the left end of the beam, are 10 millimeters deep, and they're going to be cut into the beam at a point 1 meter from where the load is applied. So they've got a 1 meter label on the picture here. Determine the smallest allowable width of the grooves. So basically what's shown as 2R in this picture over here. Figure out that smallest width. If the allowable stress in the bar is 150 megapascals. Neglect the effect of shear stress due to bending. So we didn't calculate shear stress due to bending at all before in our beams that were in bending flexural stress. So we're not going to do it now. All right, so I think there's a couple of things in here that we need. We've got the 180. We've got the 10 millimeters labeled on the picture here. We just need the 150 number. 150 megapascals is our allowable stress. So we can go back over here, I think. Okay. All right, so this one, well, they gave us the diagram. I'm going to have to move this over so I'm not covering it up. Huh? There we go. They gave us the diagram that they want to use. And basically, we just need to back out what the radius of these little notches or these grooves needs to be, or can be, the maximum it can be. And we have the other detail that sigma allowable is 150 megapascals. Let me just check that to make sure I didn't misremember that somehow. 150 megapascals. All right. Everything else is labeled on here. All right, so this would be like a beam that has a flexural stress, and we're going to calculate that. So that would be sigma equals m times c over I. The bending moment m that's applied is coming from the fact that we've got 180 Newton force that's 1 meter away from this little location. So the bending moment on this notched area is 180 Newton meters. So we got that. Whoops, 180, not 18. 180 Newton meters. C is going to be, if you look, they actually even have C labeled. So what they're showing right here, where I'm drawing the blue hatches, is the cross section. So it's a rectangular cross section, but we do have to account for the fact that where we're interested, these notches make it narrower. So, and they've got C labeled right there, which is, well, we've got D of 60 millimeters, and then each of these notches is 10 millimeters. So the distance from here to here is 40 millimeters, which would make C half of that, which would be 20 millimeters. And then a little bit off the bottom there. There we go. I, this is a rectangle. The rectangle that I shaded in blue is what I want the moment of inertia of. So if you don't remember the moment of inertia of a rectangle, you have to go to one of your reference charts to look that up. I do happen to remember it's I for a rectangle is BH cubed over 12. Where B is actually labeled B. Sometimes the label letters don't match up what the variables are, but in this one they actually match up. So B of 9 millimeters, 0.009 meters. H is the 40 millimeters, 0.04 meters. BH cubed though over 12. That's not a 6. That's a parentheses and a 0. There we go. And there's a decimal point in there that kind of got lost. Okay, now we need our stress concentration factor. So we've got our little chart here, and we have D over D again. These are actually the same as they were last time, 60 over 40. So 1.5. These are really close together, right? So it'll take, I don't know if I can even shade them in, but it's again, here it is right here. So it's the third one. No, actually that's the second one in our little set, I think. Well, no, there's a one that's kind of short over there. So it's the third one down. It's one right in the middle. So that's the trace that we need to be on. R over D. R for us is, we don't actually know that, do we? So R over D. So, well, the lowercase d is 40 millimeters. So we can't go any further that direction because we need to know R. So what we're going to have to do is we're going to have to back out the stress concentration factor and then kind of use our stress concentration chart in reverse. So let's go over back to our equation that we were writing. Sigma allowable is 150 times 10 to the 6 pascals times some stress concentration multiplier K. We don't know what it is, so K. Times the equation for our stress, 180 Newton meters, times, let's convert that over to meters, so 0.02 meters over the moment of inertia for the rectangle, 0.009 meters times 0.04 meters cubed over 12. So the only unknown in our equation, which kind of scrolled off the page here a little bit. Let's see if we can reclaim it somehow. Where's my... If I can move it over a little bit. There we go. There we go. Perfect. The only unknown in this equation is K. So let's see if we can solve for K. All right. So I've got 180 times 0.02 times 12 divided by 0.009 and divided by 0.04 raised to the third power. And then divide 150 million by that number. I get 2. So that's a nice even number. Kind of makes me think I'm probably doing it right if I get such even numbers. All right. Let's see if we can zoom in on this. Do I have a way to zoom in easily here? I don't really. We can make this bigger temporarily. It's kind of going to throw everything off, but we need to be able to find that value for K. And I think I'm actually going to have to slide it over a little bit. Wow, everything's in the way. Let's erase that one. All right, so here's the 2. So that's easy enough. And we're on this trace. Oh, look at that. That lands perfectly on the 0.1 R over D. So that helps us out. All right, let's undo all of that. So 0.1. There's where we were. So now we can go back over here and say that R over D equals 0.1 equals R over 40 millimeters. So therefore R must equal 0.1 times 44 millimeters. Now I think they actually weren't asking for that though. The problem is asking for determine the smallest allowable width of the grooves, and you can kind of see that here. That is 2 radiuses, so 8 millimeters. Why don't we plug in 8? Oh, it even says 2R. This one's kind of set up to be really straightforward. Let's see if we're correct. Yes, we are correct. All right. So those are 2 different styles of stress concentration factors. None of them are really complicated. Now you could certainly have these. The problems here we selected are very much like the charts. The notch here looks really like the chart picture does here. The diagram of this one looks almost exactly like what's on the chart. It's not always going to be in the real world where your actual object that you're working on looks exactly like the picture in the chart. So you're going to have to make some approximations or whatever of that geometry. But these are useful. This process is useful for going in and maybe you do want to do some kind of simulation work, finite element work, and this will give you a first pass that's relatively easy to calculate, that you can compare your simulation to the stress concentration factor and make sure that you're at least in the right ballpark on your simulation. It's super easy to create a simulation, hit run, let your computer do some stuff, and then an answer pops out, and you don't actually know that that's the correct answer. It just is what the computer said. So it's really important to be able to go back and get a ballpark number on your simulation that you want to run, so that you know that your simulation is more or less predicting the same things that a theoretical approach would predict. Okay, I think that probably is about all that we need to know at this level for how you operate a stress concentration chart. The biggest thing is making sure you don't misuse one of the charts. Like think of this chart and apply it to a shaft that has the same kind of shape to it. So you do have to make sure you're using a chart that matches a flat bar when you have a flat bar, or a chart that has a shaft in it when you have a shaft. So that's kind of the only difficult part of it, is making sure that you match up the right geometry with the right chart. I guess these have also been kind of contrived to land right on convenient locations on the chart, so that you're not really confused about estimating between lines or interpolating or anything like that. But they still get the point across of what you need to be doing. So hopefully that will help. You should probably have one of these on exam 3. Next week, that's basically all we have. We've got the retakes, we've got the exam 3, and then we've got the last day for turning in your group projects, and all the little bits of homework that you have left hanging out there to do. There will be one last homework. I think it might be number 22. I don't remember the number for it, but that covers some of this stuff, I believe. Maybe I should check that before I tell you that that's true. 22 is, yes, actually that's the same problem we just worked. So with pretty much a little bit different factor of safety and a different ultimate strength. So pretty similar problem. And then there were 3 of these? Yeah, there were 3 of these. So finish that up. Monday, if you're not interested in retaking either exam, then you got a day of free from this anyway. You don't have to do anything with this. Wednesday we'll do exam 3, and Thursday is turn in the reports from your group, and should be good. Hope y'all enjoyed these lectures and learned a little bit of statics, mechanics, and hopefully they'll serve you well for whatever you end up doing in the future as far as statics and mechanics. For some of you, this might be the whole bit of statics and mechanics that you get, depending on what major you are. If you're civil or mechanical, you'll certainly do more than this. This is only the beginning of what you'll do. So we will see you next time. I'll see you in Zoom for the exams, and let me know if you have any questions.